SwayamPrabha. Digital India. Educated India.
Okay, welcome everyone. So, we will in the last lecture we ended with an important theorem, which was the theorem of Weierstrass. Weierstrass was a great analyst. He had many theorems to his name. So, the particular one I am referring to is the following, that let S be a subset of Rn, be closed and bounded. Let F from Rn to R be continuous. Then the claim was that there exists that a point that attains the minimum, the infimum of F in the set. So, there exists an X star in S such that F of X star is equal to the infimum of F of X as X ranges in S. So, in this case we said the word we used was that the infimum of F is attained in S. Now, because a problem of minimizing a function F can always be converted to a problem of maximizing another function, and when by just changing F to minus F, and changing F to minus F preserves the continuity of F. So, if F is continuous, then minus F is also continuous. Okay. So, that does not change the continuity. So, consequently, this theorem also gives us for free that there exists another x, say let us call this x hat, suppose x hat in S such that F of x hat equals the supremum of F over S. Okay, so, both the infimum as well as the supremum is attained. Now, let us just give some more intuition on what this theorem is actually doing, because you will get an idea from this about what is happening when your algorithms in optimization do not converge and so on. So, I had told you two examples last time. So, let me draw those two examples again. So, one was this, an example of this function. I am plotting here on the x axis. The function is a function of real numbers. So, this is what I am plotting here is just the x axis of real numbers. So, I am plotting R. So, the function is like this, and there is some point A where the function value jumps to the bold point there, this red point, that is the value of the function at A, and then after that the function then increases this way. Okay. So, the function decreases till this point till A, but at A its value is, it jumps and then it increases in this sort of fashion. Okay. This is one case. Another case is this case which I drew last time, which was the case of where the function is e to the minus x. So, here f x equals e to the minus x, and we took s as the non-negative reals. So, what is the infimum of f here? The infimum of f in this case, in the second case, the infimum of f in the second case is 0. So, as okay, the least possible, the infimum of f over s is 0, and we found that there was a problem here, that there was no x star for which f of x star equal the infimum. Here is now a third case on top of that. So, suppose I consider the interval from just 0 to 1, but I exclude the endpoints. Okay. So, I have an open interval from 0 to 1. So, that is my s is my open interval from 0 to 1. And let us just simply take this sort of linear function that keeps decreasing this way. Now, in each of these cases, can you tell me what the infimum of f is and whether it is attained? So, if you recall, the infimum of f in this case was this height, right, this height here. This here is the infimum of f. So, I am taking s as, let us say, r for simplicity. In this case, the infimum of f in this case is 0. What is the infimum of f here? What is the infimum of f in the third case? The infimum of f in the third case is again this height. And now, in each of these cases, let us ask if the infimum is attained. So, what happens in this case? In this case, in the first case, okay, in the first case, let us call this case 1, let us call this case 2, let us call this case 3. So, in case 1, what happens is the infimum, the function is tending towards to becoming smaller and smaller as you approach a from the left. You get lower and lower values, but at a the value jumps, right. So, the problem in case 1 is you can say is a discontinuity in f. What is the problem in case 2? The problem in case 2 is that the infimum is 0, but the infimum is attained quote unquote at infinity, right, and infinity is not part of our domain. We are looking at only real numbers, right. So, the problem here is that the domain is unbounded. Domain, or more specifically, let us say S is unbounded. What is the problem in case 3? Is the infimum attained in case 3? Again, what you see here is, you see that the function value decreases as we go down here, keeps decreasing as you keep going closer and closer to 1. The infimum is eventually the limiting value of this height. it would have been f of 1 if f of 1 was defined in the same way and if 1 was part of the domain, but then 1 is not part of the domain, right. So, what is the problem in this case? The problem is that the S is the boundary of S is not included in S. So, S is not closed. So, what if you go back, if you see these three issues that have cropped up, one is discontinuity, the other is unboundedness, third is closeness. If you plug all three of them, what Weierstrass theorem is telling you is that if you plug all three of these deficiencies, then there is no problem. After you are assured that the infimum will be attained, right. So, if a function, if your set is closed and bounded, if your function is continuous, then your infimum and also the supremum of your function on the S will be attained. This is what Weierstrass theorem is telling you. Okay. This also brings me to a couple of other points which we should mention, because eventually the geometry of optimization depends on the kind of sets over which you are optimizing and the kind of function over which you are optimizing. So, let me mention a couple of other things. Remember what the definition of an open set was. An open set S is said to be open if there exists a radius r greater than 0 such that b of x comma r is completely included in S. S is said to be open if for all x in S there exists a radius r greater than 0 such that b of x comma r lies completely in S. Now, if a set is not open, then we can in some cases extract those points around which such balls exist. That is what is called the interior of a set. So, I will define that. So, let C subset of R n be any set the interior of C denoted in this way. It is denoted usually by C with a little circle on top. This is simply the union of all sets S that are such that S is open and S is contained completely in C. So, take all the open sets that are completely contained in C, take their union, that is what is called the interior of C. And there is an analogous notion of what is called the closure of C, that is denoted by this C with a bar on top. This is called the closure of, and this is the intersection of all sets S such that S is closed and S contains C. So, the interior of a set is the largest possible open set you can fit inside the set. Do you see that the interior itself is an open set? Because it is a union of arbitrary open sets. So, the interior itself is an open set. So, the interior is the largest, therefore, the largest open set in C, and the interior and likewise the closure is also a closed set, because it is an intersection of an arbitrary number of closed sets. So, it is the smallest closed set containing C. Okay. Now, if you consider this set, which is, let us define this, let us denote this by del C like this. This is what is called the boundary C. This is simply defined as C closure minus C interior. So, which means you look at the closure and remove from it all points that are there in the interior. Whatever remains is what is called the boundary of C. Now, if C is itself closed, then C closure is equal to C. If C is itself open, then C interior is equal to C. Is this clear? But if C is neither closed nor open, then these may in general be different. Okay. Now, the reason I bring this up is because we have to, as we start talking about optimization problems, we have to pay careful attention to the kind of to the way we are defining this set. So, now suppose you have if you encounter an issue such as, for example, the three cases that I just mentioned, you have case 1, case 2, case 3, the way, and these are in all these cases you would have the issue, you will have the difficulty that your infimum is not being attained. So, there is no solution to there is no optimal solution to an optimization problem, either in this case or in this case or in this case. Now, the way to fix it, now in case 1, the thing, the culprit is the fact that your function has a discontinuity, right. So, you have your function itself needs a change, what you are optimizing, that itself needs to be changed in order, and you need to consider something that is continuous. How do you fix case 2? What will happen in case 2 is, suppose you run an optimization algorithm, it keeps searching for a better and better point that will give you a better and better value for f, and in the process it will keep going farther and farther and farther away towards infinity. Eventually, you will reach a stage where you have run out of the precision of your machine. If you have used MATLAB, you would have encountered this error called NaN, not a number, right. So, this sort of error, this is the sort of error you would end up getting. So, what this is suggesting is that your domain is too large, you need to plug your domain. Of course, this is not the only way, you might want to consider a different function and so on, that is a separate matter. But since here the domain is to be blamed, I am talking of the domain. So, your domain needs to be clipped, and you need to clip it at some point. You need to bound it, consider a bounded domain. The third case tells you that simply bounding it without including the boundary points is not enough. You have to make sure that eventually your domain has to be both closed as well as bounded, right. So, if your boundary points are not included, you again have this problem that your algorithm keeps searching, goes further and further closer to the boundary, but then the boundary is not included. So, it keeps searching, it will never actually get to a solution. Okay. So, you need, so in the case, if you are in case 3, you need, what you need to do is make sure that so if you are in case 3, one simple way of fixing this would be that you make sure your set is closed, and for that all you need to do is simply take the closure of your set, right. Okay. So, now let Let us again go back to an optimization problem, and now from here onwards I am going to assume that an infimum is attained. So, if you remember my notation for when the infimum is attained, we said we will write it like this, we will call it the minimum. And so, the way we will write optimization problems is that we will write here a function f that we want to minimize subject to this condition. So, when I write subject to something, it means that this is the set over which I am minimizing, and this is the function that I am looking to minimize. So, in this, any point in S is called a feasible point. It is called a feasible point. The S as a whole is called the feasible region. Points that are outside S that means that is they belong to S complement. They are called infeasible. They are infeasible points.